In this video, we're going to derive the pullback or vector-Jacobian product rule for nonlinear system solving. Nonlinear system solving, or the solution of high-dimensional root-finding problems, can be seen as a function that takes an input, here called theta, and then solves a zero condition for its roots. It thereby, for instance, applies, or most commonly applies, a Newton-Raphson method to obtain the root of that parameterized zero condition. You will find these kind of nonlinear systems in scientific computing. So if you solve nonlinear partial differential equations, so for instance the Navier-Stokes equations, you will also find them in nonlinear optimization problems, as well as more recently in deep equilibrium models as part of deep learning. In this video, we want to look at pullback or vector-Jacobian product rules because we have that computation, the solution to nonlinear system solvings, as part of a larger computational chain for which we then want to apply reverse mode automatic differentiation on. So we need to be able to differentiate over the solution to these nonlinear systems. But first, let's look at the dimensionalities. Here we will assume that theta, or the input to the root finding problem, or this wrapper function f, is a p-dimensional vector. We will say that x is an n-dimensional vector, and as such, our optimality criterion, or the zero condition, is a function that takes both an n and a p-dimensional vector and spits out an n-dimensional vector. And the wrapper, which wraps the Newton-Raphson scheme, will then map from the theta input to the x output, so it maps from a p-dimensional to an n-dimensional space. Generally speaking, nonlinear system solving is quite a difficult task, but for our discussion here, we will assume that everything works fine, our solver converges, and we do not have any other issues to deal with. And then let me again write down the task for this video, or why we want to derive a pullback or a vector-Jacobian product rule, is to backward propagate cotangent information on the output, and the output of our function was the vector x, but now we have cotangent information, so we denote that with a bar on top, and this one is of the same shape as the primal output, so it will be an n-dimensional vector. And then we should backward propagate this to the input, and the input was the theta vector, and here we will then also have a cotangent, so I put a bar on top, and this one will be a p-dimensional vector. And now let me add a crucial piece of information, that we want to do this without differentiating through the solver, or in other words, without reverse mode AD, or reverse mode automatic differentiation, through the solver. And by through the solver, I mean that we take the Newton-Raphson scheme that we use in the primal pass in order to obtain the roots, and we view it as a chain of computations, similar as we would do it for classical automatic differentiation, and then apply all the primitive rules for the smaller operations that are part of it. But this is what we do not want to do. Rather, we want to consider the solution to the nonlinear system as a supernode in our computational graph, for which we have a custom reverse rule which does it differently than differentiating through it. This idea of differentiating through it is also sometimes called unrolling, because instead of differentiating over it and seeing the primal solution as a black box, we will unroll the iterations from the primal solution and record them and then backpropagate through them. So how do we do that? In general, we know that the rule for backpropagating cotangent information is that we will get the cotangent on the input transpose as the cotangent on the output transpose, and then multiplied with the Jacobian of the function over which we want to backpropagating. So this is df by d theta. So I already said it, this one here is the Jacobian of the function. In our particular layout here, this will be an n by p-dimensional matrix, and if we then take an n-dimensional vector and left multiply it with the Jacobian, we will get a p-dimensional vector. Of course, this will then be a row vector, so therefore we do another transpose to go back to a column vector. And since we are left multiplying a vector with a Jacobian, we also call this the vector-Jacobian product. If we were to do the unrolling with the reverse mode automatic differentiation, this one is the quantity that our AD engine computes for us. But it does so by opening the black box to this primal solver and differentiating through it. There is an alternative way of writing this down, which I think is a little bit more helpful for us later on, because if we apply the transposition on both sides of the equation, we will get that the cotangent on the output is the Jacobian with respect to theta in brackets transpose multiplied with the cotangent on the output. And here we will then have the Jacobian transpose, and as such, this one is called the Jacobian-transposed-vector product. But it is essentially the same as if we write it in that way, and therefore I will much rather refer to this as a vector-Jacobian product. Both of it are pullback operations. Okay, but saying that we do not want to do the unrolling, what is our alternative? And for this we will employ an idea that is based on the implicit function theorem, and in order to do so, we will take the total derivative of the optimality criterion. So let's take the total derivative of the optimality criterion. Okay, what was the optimality criterion? This is essentially the zero condition that has to be fulfilled in order for a solution to be a solution to this nonlinear system of equations. Okay, let's do that. And we take the total derivative of g with respect to the input theta, and then we will see that g depends on both x and theta, so it has an explicit dependency on theta, but the total derivative is resolving all the nested dependencies, and since it depends on x, there is a subsequent dependency on theta, because x is implicitly given, so obviously if you change theta, you will get a different x. If you have a different parameter to your parameterized optimality criterion, then the nonlinear root solver most likely will also give you a different solution. So we'll first have the nested dependency, partial g with respect to partial x, and then partial x with respect to partial theta, plus partial g with respect to partial theta. That's the explicit dependency. And this one has to hold to the zero matrix. And that is because our optimality criterion has to be zero. If something is zero everywhere, its derivative also vanishes. Here we might not directly see it, but the partial derivative of x with respect to theta, or this very Jacobian, is the quantity that we are interested in. So this is equivalent to df by d theta. So this one here is equivalent to df by d theta, because we can always represent the function that we're looking for with its output. So the derivative of the output with respect to input is equivalent to the derivative of the function with respect to its input, kind of loosely speaking. Okay, so let's rearrange for this interesting quantity that we have here. So we will get that the derivative of f respect to theta, which we said is equivalent to the x by d theta. And here we also see this is a Jacobian. It's most likely also a dense matrix here. And it is given as minus dg with respect to dx in brackets inverse multiplied with dg by d theta. So we will see it requires the inverse of a Jacobian, or in other words, when you see the inverse of a matrix, this is the solution to a linear system of equations. Okay, now having found this expression, let's plug it back in. And by plug back in, I mean the general definition of the vector-Jacobian product. And then we see that theta bar transpose is given as x bar transpose multiplied with that expression, so minus dg with respect to x in brackets inverse times dg with respect to theta, closing brackets. However, let me instead use the other definition of the vector-Jacobian product as being the Jacobian-transposed-vector product, because then it becomes a little bit more clear what we will identify. This is, in that sense, equivalent to saying that theta bar is this quantity transposed, so minus dg by dx in brackets inverse times dg by d theta in brackets transpose times x bar. So I just copied the other definition that we have here and plugged in the quantity that we found. And then let's apply the transposition rule for multiplication of matrices, and this will change the order and apply the transpose to all of them. So we will get this is minus dg with respect to theta in brackets transpose multiplied with dg with respect to x in brackets to the minus t, so it's the inverse of the transpose matrix multiplied with x bar. And here again, this, since there's no -1 in the exponent, but it's still the inverse, which again shows we have to solve a linear system of equations. And let me make that a little bit more verbose by defining this one to be a vector lambda. So the vector lambda is given as dg with respect to x in brackets to the minus transpose, so inverse of the transpose, multiplied with x bar. So we find lambda, which we might also call the adjoint variable, but you can also think of it as an auxiliary variable. And we find that in that we solve this linear system of equations. So a linear system of equation solve. And let's also make this a little bit more clear that it is a linear system. If we multiply with dg by the x to the transpose from both sides, we will get that this is dg with respect to x in brackets transpose times lambda is x bar. And here we also clearly see that lambda is of the same shape as the output, or also the cotangent on the output. So this lambda here, so lambda is another n-dimensional vector. Okay, when we have this one replaced with lambda, we see that the propagation from lambda to the theta bar, where we finally want to end up, is just the multiplication of dg with the theta transpose and then with lambda. So here we will get that theta bar is minus dg with respect to theta in brackets transpose multiplied with the vector lambda. Okay, so this is kind of a two-step process. So we'll first take the cotangent, find the lambda by solving a linear system, and then use the lambda to propagate it to the cotangent on the out. And in that sense, we can maybe also make this even more verbose and say that lambda, so this multiplier, is given as the solution to the linear system of equation, dg with respect to x in brackets transpose times lambda is x bar, and solve this one for lambda. And with the help of lambda, we can then write the full pullback rule. So the full pullback rule, or in other words, what you might want to implement in your reverse mode AD engine as a custom reverse rule, in that the backward rule on the function f, and the function f was the nonlinear root solver, with the primal information theta, as well as cotangent on the output x bar, is given as first the primal computation. So we will evaluate f on theta. So in other words, we have a very concrete point for which we want to query our root solver. So this will then yield us the primal solution x. And then we will make another operation which will be minus dg with respect to theta in brackets transpose multiplied with the adjoint variable lambda. And this adjoint variable lambda comes from that linear system of equations, which is a little bit hidden here, but of course that's also an essential step in order to pull back the cotangent information. And I think that's a really interesting insight, because similar to what we've also seen with the push forward rule, we need to solve an auxiliary linear system of equations in order to either forward propagate tangent information, or here in our case, backward propagate cotangent information. I believe the interesting insight is that this is a linear system of equations, not a nonlinear system of equations. And this nonlinear system, which was our original primal problem, is quite a tough one. And oftentimes, if you employ a Newton-Raphson scheme, linear solvers are a sub-operation of it. So, for instance, it might take you 20 Newton-Raphson iteration, then in each iteration you would have to solve at least one additional linear system of equations. So it takes you maybe roughly 20 linear systems, and then it just takes you one more linear system to propagate tangent information. So either forward mode with tangent information or backward mode with cotangent information. And that's quite a cool insight. And although, of course, any kind of solver, like also with the linear solver, could come with its additional difficulties. I think there's now one question left in that, okay, so we know how to kind of backpropagate through this operation or over this operation, but how do we obtain these additional derivatives? So here we will have a dg by the theta multiplied with lambda, and here we even have to solve a linear system that involves the Jacobian as the system matrix. Maybe let me note down this question with how to obtain the additional derivative estimates. And here we will call back into our reverse mode AD engine for which we defined the rule in the first place, because we assume that our optimality criterion can just be reverse mode AD'd. So in essence, these are just vecor-Jacobian products or pullbacks. So these are just vecor-Jacobian products or pullbacks. Maybe in order to be a little bit more precise, they are Jacobian-transposed-vector products, but this is identical. This is essentially what your AD engine can give you. Let's say this again, that we can get by calling back into the reverse mode AD engine. And that should answer how we can do this second step. So this is just one Jacobian-transposed-vector product. But the linear system is a bit more tricky. Let me also note down how to do that. So to solve the linear system, and the linear system was given in the way as vg with respect to x in brackets transpose multiply with lambda is equal to x bar. So x bar is the right hand side, and we will solve for lambda. If you would solve this kind of with a dense solver, you need to be able to access the full Jacobian matrix. Oftentimes this is not necessarily what you want to do. So instead you could use a matrix-free linear solver. So use a matrix-free linear solver, and there are a lot of options. Classical ones would be a conjugate gradient one if your Jacobian matrix is symmetric positive definite, or just in general a GMRes method. And then we have to present the matrix vector product, and the matrix vector product is basically the essential ingredient in order to get the CG or the GMRes method to work as the vecor-Jacobian product. So as the vJp, the pullback, or the Jacobian-transposed-vector product, however you want to call it. And we do that by the help of reverse mode AD, by the reverse mode AD engine. And another crucial information, and the same holds true for this Jacobian vector product, in that we evaluate it at the primals. So evaluate it at the primals, because here we want to do the Jacobian vector product of a function g, which takes two inputs, and these two inputs, or these primal inputs, need to be defined in order for the function to properly work in the Jacobian-transposed-vector products. But this is what we already did, because we solved the primal problem beforehand. So we know the concrete theta, we know the corresponding concrete x, so we can also evaluate these Jacobian-transposed-vector products. And this again highlights the idea of automatic differentiation, that you will always need a primal pass and need to save intermediary values. Okay, let me quickly summarize that. Here in that video we looked at a custom pullback or vecor-Jacobian product for the solution to nonlinear systems of equations, which appear in nonlinear PDEs, nonlinear optimization problems, or deep equilibrium models. For a lot of the cases, we are interested in not just solving the primal problem, but also in the propagation of tangent information. So for instance, in PDEs, you might want to do some design optimization. So there are two main options. We could either use an unrolling approach, which sometimes might not even work, or we alternatively employ the implicit function theorem, and then we find out that a reverse mode rule can be given by the help of a solution to a linear system of equation and the evaluation of some vecor-Jacobian products on the optimality condition. And so we can then define a full pullback rule that evaluates that and calls the linear solvers. And just again to remind you, oftentimes a Newton RefSim team does a couple of linear solves, and here we only need to do one additional. So maybe if our primal takes 20, 30, we just do one more, so we do 21 or 31, and then also be able to propagate tangent information or cotangent information once. A big thanks to all the patrons of the channel. If you also want to support my vision of free education on these advanced mathematical topics, you will find the link to the Patreon page down in the video description. I hope you enjoyed that video. If you did, then please leave a like and consider subscribing to the channel. There's more awesome content on primitive rules for AD, implementations for automatic differentiation, or also how that all fits together and how to build differentiable simulation engines in order to do really cool learning stuff. Here you will now see similar videos, and I hope to see you in one of the next videos.